Hi, welcome to Chapter 19, Chemical Thermodynamics, Overview Part 1. We'll talk about spontaneous processes, entropy and the second law of thermodynamics, the molecular interpretation of entropy, and the third law of thermodynamics. So just to remind you, way back in Chapter 5, we talked about how energy cannot be created or destroyed. And this is the first law of thermodynamics. Your total energy of the universe is a constant. Energy cannot be created or destroyed, but it can be converted from one form to another or transferred. At the time, we also mentioned enthalpy and entropy very quickly. So let's just refresh our memories. Enthalpy, represented with the letter H, is the heat absorbed by a system during a constant pressure process. And entropy, which is represented with a capital S, is the measure of the randomness in the system. Both of these play a role in determining whether a process is spontaneous or not. What is a spontaneous process? So if you look in this diagram here, we have a yellow gas in bulb B and nothing, a vacuum in bulb A. If we open this valve, I think we all can visualize that the yellow gas will flow over and fill both of these containers as is shown here. Since it does that without any outside intervention, that is called a spontaneous process. Okay? Now, try to envision getting all the gas back into B. Will it do that on its own? No. So that is why that is not a spontaneous process. So spontaneous processes are those that can proceed without any outside intervention. Another example of a spontaneous process is a nail rusting. Okay, so here's your nail and it rusts. Now, will this rusty nail ever convert back to the original? No, so that is a non-spontaneous. Okay. Do these reactions need to occur quickly? No. Spontaneous does not describe the rate of the reaction. Okay, the rate of the reaction is described by chemical kinetics. This chapter is on thermodynamics. Okay, that all of the stuff we're going to talk about in thermodynamics does not tell you how fast the reaction is going to occur, just if the reaction can occur. So spontaneous just means that the reaction will occur without any outside assistance. Is the reverse reaction also spontaneous? And the answer to that is no. Processes that are spontaneous in one direction are non-spontaneous in the reverse. So let's summarize our spontaneous processes. And here's a good picture to help you visualize it. When you drop an egg, it will spontaneously fall down and hit the table and break. Now, will this egg put itself back together like Humpty Dumpty and go back up into the hand? No, so that is non-spontaneous. So, spontaneous processes proceed without outside assistance. Processes that are spontaneous in one direction are non-spontaneous in the reverse. Now, don't confuse if something is spontaneous with speed. Spontaneous does not mean fast. There are fast and slow reactions that are spontaneous. Also, don't confuse non-spontaneous with meaning it is impossible. A non-spontaneous reaction can occur, but you might need some outside forces to help it along. So energy can be used to make some reactions spontaneous that otherwise would not be. So just because it is non-spontaneous doesn't mean it's impossible to happen. Some experimental factors will affect the spontaneous processes, and those are temperature and pressure. So processes that are spontaneous at one temperature may not be at others. And here is an example. In this flask we have ice. In this flask we have water. If the temperature is above 0, the ice will spontaneously melt into water. If the temperature is below 0, the water will spontaneously freeze into ice. So the spontaneity of this reaction depends on its temperature. What is a reversible process? Remember, we said that all spontaneous processes are, the reverse is non-spontaneous. So what does reversible mean? In a reversible process, the system changes in such a way that the system and the surroundings can be put back to their original state by exactly reversing the process. So whatever you did initially, you do the opposite and you'll get right back to where you started from. That is what reversible means. An irreversible process cannot be undone by exactly reversing the change to the system. Spontaneous processes are irreversible. Here is a diagram of an irreversible process. Here you have gas in this chamber, and it has this like movable wall or partition. You pull that out, and the gas will fill the whole container. If you want to put the gas back in this half of the rectangle here, you have to push it back there. So you have to apply work to it. Now, when it filled the container, there was no work being done. So this is not the exact same process in reverse. So this is an irreversible process. It doesn't mean it can't be done, but it just means that in this case, you have to add work to do it. So it's not exactly the same in the reverse order. So let's summarize reversible and irreversible processes. A reversible process, the system changes so that the system and the surroundings can be returned to their original state by exactly reversing the process. Okay, and this is important. If your system is reversible, you will maximize the work done by the system on the surroundings. Okay, so you will maximize the work done for reversible processes. In an irreversible process, it cannot be undone exactly by exactly reversing the changes to the system, or it cannot have the process exactly followed in reverse. It cannot, okay? Also to note or remember that spontaneous processes are irreversible. So let's get back to our entropy. Remember, entropy is represented with the capital S. Entropy can be thought of as a measure of randomness of the system. It is related to the various modes of motion of the molecule. Like total energy and enthalpy, entropy is a state function. And remember, we talked about state functions way back at the beginning of the year. And a hint I gave you back then is if your variable is a capital letter, then it most likely is a state function. But what does state function mean? It is independent of the path. So if I want to get my change in entropy, all I have to do is take where I ended minus where I started. I don't care what path I took. This will always be the same if I take the final entropy minus the initial. That's what a state function means. For a process occurring at a constant temperature, so you might see this a lot in this chapter, that means isothermal, where iso means same, and thermal means temperature. So at constant temperature, the change in entropy is equal to the heat that would be transferred if the process were reversible, divided by its temperature. So right here is your relationship. This occurs at constant T. And T has to be in Kelvin. So the second law of thermodynamics. There are three of them, states that the entropy of the universe increases for spontaneous processes, and the entropy of the universe does not change for reversible processes. That means reversible processes, another way you can think about it, is our processes that are in equilibrium. Remember our equilibrium chapter? So the entropy of the universe increases in a spontaneous process, which is irreversible. Remember, spontaneous, irreversible, same thing, right? The result is the following relationship. If you have a reversible reaction, the entropy of the universe, this is what UNIV means, is equal to your system entropy plus your surroundings. And when you do that, that is equal to 0. For irreversible processes, your system plus your surroundings is greater than 0, so your entropy is increasing. So the last truth means that as a result of all spontaneous processes, the entropy of the universe increases. And remember, spontaneous is irreversible. So we've thought about entropy on the macroscopic level. Let's think about it on the molecular scale. And that's what Ludwig Boltzmann did. You might recognize his name from the Maxwell-Boltzmann distribution. But he described entropy on a molecular level. And here is his tombstone. And you'll notice this equation is engraved onto his tombstone, where S is your entropy. So let's talk about this entropy on the molecular scale. Let's look at this diagram right here. So here I have two gas molecules in this bulb. I open the valve, and I have 4 possibilities of what will happen. Okay, so when we're thinking about it on the microscopic scale, statistics comes in play here and is very important. So here we have 4 possibilities for our two gas molecules. So when Boltzmann kind of looked at entropy on the molecular level, he kind of did this statistical analysis. And basically, the two molecules start on one side above here. What is the likelihood that they will end right back where they started with after you open the valve? So the probability would be 1 over 2 squared. And this might not really draw your attention to it until we start thinking about moles of gas. So if we have 1 mole of gas, that is Avogadro's number of particles. 1/2 raised to Avogadro's number is effectively 0. So after you open the valve, the chances that these two gas molecules end up right back where they started from is basically 0. Okay? So gases will spontaneously expand to fill the volume given. And the most probable arrangement, when you look at the statistics of it, is when you have approximately equal molecules on each side. So he developed a whole field called statistical dynamics. So thermodynamics will look at the bulk properties, the macroscopic, the big picture. And we have seen what happens on the molecular scale, and how do they relate? Well, if you could use statistics and probability to rate them, this field is called statistical thermodynamics. And what Boltzmann did was he defined something called a microstate. And a microstate is a single possible arrangement of position and kinetic energy of molecules. Or a simpler way of saying it, it's like if you could take a picture of your molecules. It's a snapshot in time of their arrangements of those particles. And then think about taking a picture over and over again, and the molecules are constantly moving. So each picture that you took where they're in a different position is a microstate. Because, and you could kind of visualize it, because you would be taking so many pictures, so many snapshots, it's hard to, you can't look at every one of them. So what Boltzmann did was he defined his variable W, and he used it to represent the number of microstates. And entropy is a measure of how many microstates are associated with your macroscopic state. So the larger the number of microstates, the greater the entropy. The larger the number of being able to arrange your particles, the greater your entropy. The connection between the number of microstates and the entropy of the system is the equation that is engraved on his tombstone. Here we have natural log. On his tombstone it says log, but it was referring to the natural log. Okay, where K is Boltzmann's constant. Makes sense, it's named after him. And since entropy is a state function, the final entropy minus the initial will give you the overall change. So if we kind of plug using this equation, get our delta S, we find that it would be Boltzmann's constant times the log of the final over the initial. If your final number here is larger than your initial, then your entropy is increasing. So as you get more microstates, the higher your microstate, the number of microstates, the greater your entropy. And in this case, the more disorder. How do volume and temperature changes on the system affect entropy? So if you increase the volume, and I think you can kind of picture this, if you give gas molecules more space, they will move around more, and you will have more of these microstates. So if you increase the volume, there are more positions possible for your molecules, which result in more microstates, which increases the entropy. If you increase temperature, now your particles have more average kinetic energy. That results in a greater distribution of the molecular speeds. Think about your Boltzmann's distribution, right? Where this is low temp. And what happens as you raise the temperature? This is high temp. Okay, you have a greater distribution of the speeds. Therefore, you have more possible microstates, increasing your entropy. So as temperature increases, entropy increases. As volume increases, entropy increases. So here's kind of a visual way to kind of talk about it. Molecules can exhibit several types of motions. There's translational, where the entire molecule moves from one place to another. There's vibrational, which is the periodic movement of atoms within. So if you look here, they can move up and down like this. They can move back and forth like that. The angle can kind of vibrate. These are all your vibrationals. Then there's your rotational. That's if you spin the molecule around a certain axis or rotate it about the pi bonds. Okay. Now, interestingly enough, if you have a monoatomic gas, it only has translational motion. Because it's not bonded to anything, okay? It can't vibrate up and down or have bound angles that are vibrating. And if you try to rotate it, it looks the same. It's just a sphere, right? So entropy on the molecular scale. So Boltzmann envisioned the motion of a sample of molecules at a particular instant in time, and he basically said take a snapshot of this, and he referred to that snapshot as your microstates. And if you have more atoms, that means you have more microstates, which means you have higher entropy. You have more possible molecular motion. So you have higher entropy. So each thermodynamic state has a specific number of microstates, which he termed W. And basically he said entropy is just equal to Boltzmann's constant times the natural log of W. And here again is Boltzmann's constant. So this is a more visual explanation of that previous slide that was very wordy. So let's kind of wrap it up here a little bit, summarize. The number of microstates, and therefore the entropy, tends to increase with increases in temperature. If you increase the temperature, you're going to increase entropy. And increasing the volume, they have more space to move around, more microstates. And the number of independent moving molecules. So the more molecules you have, the higher your entropy. And the freedom of motion within these molecules. So that is why your gas, your entropy of your gas, this is gas, this is liquid, and this is solid. Gases have the highest entropy. Solids have the lowest because their motion is limited in the solids, whereas gases, they are not limited as much. What happens when you make a solution? Well, in general, when a solid dissolves in a solvent, you're going to increase your entropy. So, in general, entropy will increase when gases are formed from liquids and solids. So if you look here, here is your solid, here is your gas. Your entropy is increasing as you go from solid to gas. You have more freedom to move. The more freedom to move you have, the higher your entropy. Liquids or solutions are formed from solids. So if you take a solid and you liquefy it or you dissolve it, you're going to increase entropy. If the number of gas molecules increases, you're going to increase entropy. And if the number of moles increases, you're going to increase entropy. Take a look at this diagram here. Here we had 2 moles of gas. Here we have 3 moles of gas. This has a higher entropy. So let's summarize entropy. Entropy increases with an increased number of moles. So if you break your particles into smaller pieces, your entropy is going to increase. Entropy is greater for a gas than for a solid and a liquid, okay? So a liquid is greater than the solid, and the solid is the lowest. Entropy increases with more moving parts or atoms in a molecule. The more atoms you have in a molecule, the more possible movements you could have, the higher your entropy. Entropy increases with temperature, although this is minimal and is mostly ignored. And that is the end of Overview Part 1.